And just like for everything else in statistics, well, if there is a graphical way to display it, there's also a numeric way to just summarize what that graphical display tells us. So that's what the coefficient of determination does. The coefficient of determination is r squared. In fact, almost everyone refers to it as r squared. I did not even know that it had a different name than r squared until I taught intro stats and saw this coefficient of determination for the first time ever. It's literally just the correlation coefficient squared. That's it. It's almost always given out as a percentage. There is some software packages that give it out as a decimal. And it's super useful because it gives this percent of the variation of y that can be predicted using the other variable. Now, so let's put a pin in this. When we get to the interpretation, we'll chat more about what the hell that means. But it's basically a measure of how good our predicted power of our line is. And 0 means that it's telling us absolutely nothing. The line is useless. Up to 100 means the line is telling us everything we need to know, because the only way to get 100 would mean that our original r was 1, which meant everything fit directly on the line. So in terms of this the coefficient of determination, this is how you're going to have to be calculating r and r squared, as being using one to go back and forth. So if I ask you to find the coefficient of determination on an exam, that means you have the correlation coefficient somewhere. So one thing you might want to do, I do like to have this as a percent, so that maybe should have been there. And then you might have to go the other way. This is a little more common, and this should be on your note card perhaps, where you can go backwards by square rooting your r squared. But the one issue is for this, two pieces. One, when you square something, you lose whether it was positive or negative, right? So you need to look at something, whether it's the slope of the line or a scatter plot, to figure out whether your original relationship was positive or negative. So this will usually be the same as the slope. And the r squared, remember, r has to be between -1 and 1, which means you got to enter this as a decimal. I get real upset if you tell me that r is like 8.3, because that is not possible, and I will dock you more points than if you hadn't even written a value there. I mean, I can't dock you more points than it's worth, but the partial credit that you might have gotten sort of goes out the window when you do something like that. So that's the calculation. Let's chat a little bit about that interpretation. So the interpretation of r squared, this goes along with that, that bullet point I circled on the previous page. It's the percent of variability in our y that can be explained by the regression line, essentially. So what does this mean? All right, I'm going to give you a very complicated, overly simplistic, but still very complicated explanation. And if you don't follow, I promise you'll be fine. Nothing in your life will be different. But if you do, power to you. So looking at this first example, we have stopping distance versus speed. So obviously, the faster you're going, the further your stopping distance is. So if we looked at this, let's just look very, very simply at the range of our data. Or the range of our y's, right? Because we're talking about the percent of variability in y. And remember, variability is just the spread. Now, technically, we're talking standard deviation, but standard deviation is hard to visualize, and I'd have to do some crazy calculations. I'm just going to look at range. It looks like our range is about 120, right? 120 minus 0, about 120. Now, if we look at the residual plot, now we've taken this speed, if we take this line out, and we've managed to get our predictions. You know, we have some bad ones. These two happen to be bad, these two here. We have some where we grossly over-predicted how long it would be to stop, right? But we've managed to get this to a 40 to, let's say, -30. So this now has a range of 70. We've decreased the range, right? We've gone from something that had a range of 120 to now a range of 70, because we're saying we know the values plus or minus essentially 40 to 30, depending on the direction. So that means we have explained 50 points of the range out of the original 120. That's essentially what we're talking about, this percent of variability explained. Is like, how much did I improve upon what the hell Because right now, if I didn't know the speed, I would say the stopping distance for your car is somewhere between 0 and 120 feet. I'm assuming those are feet. Maybe it's yards. I have no idea. Again, we should have freaking units. But if you tell me your speed from 0 to 25, with the line, I can now tell you your speed plus or minus, right, a certain value. So it's just sort of about how much better my predictions can be. So again, if you didn't get it, do not worry. It doesn't matter. What you really need to know is, one, you could write this on your note card. But two, what the heck that R squared is telling us. And basically, the closer it is to 100, the better our model is at making predictions, the more that we can kind of believe in that slope interpretation. So we have this sort of set of criteria here. Excellent would be greater than 80. Then we have good, fair, and weak. And I do have one quick anecdote from when I was at UCSD. I had done this crazy model that looked at, what did it look at? It looked at like all these different childhood risk factors. We made like a scale or score of like out of 4 or 5, and how they affected cortisol levels when someone was 55. So it was like childhood risk, which was like all about like mom's education, like dad's socioeconomic status, like a bunch of crazy stuff. We then did like this crazy mediation model, because like, and we said like, okay, well, this then goes through midlife SES. I don't remember exactly what the crazy model was, but we made a crazy structural equation model and did a whole bunch of analyses, wrote up a whole paper. And then all of a sudden one of the co-PIs came into my office and she's like, you know what we didn't do? We didn't get an R squared. We didn't see how good our model was at predicting midlife, age 55 cortisol based on childhood risk factors. And I was like, oh, right. I'll do that. It's a fairly straightforward calculation. So I went, did the calculation, and then like wandered back into her office with my tail between my legs, because what I found was an R squared of like 1%. I don't remember what it was. It was like 1 or 2%. It was terrible. It was like, I was ashamed and sad. And I was like, we wrote an entire paper for this much, for this R squared. Like this, to me, based on everything I know about statistics, means that this is nonsense and we should throw this paper away. And she's like, oh, that's great. That's great. I can't believe we managed to describe 2% based on this childhood risk. And I was like, oh, okay. Different interpretations. Great. But, so as much as we use these guidelines, and these are good guidelines, there are situations where an R squared that's lower, is still not necessarily terrible. I think this one was still terrible. But, if you can describe a certain amount of the variability and it's something that you thought was sort of tangentially related, maybe it's not so bad.